some equations make more sense to represent in a cylindrical coordinate system than they would in a Cartesian or rectangular coordinate system. And oftentimes you'll have an equivalent representation, but it could be very ugly in one and very simple in the other. So I want to show you some simple examples of things that we've seen before that are represented in the different coordinate system types. The first one is this circular cylinder. And in the case where the radius is 3, we have x squared plus y squared equals 9. That's your standard Cartesian coordinate or Cartesian representation. But then you also have a very simplified version, r equals 3 in cylindrical coordinates. And if you think about it, that makes sense because at any given point, every point on this cylinder has a distance of 3 for its projection in the xy plane. So its distance from the z-axis is always 3 throughout the entire cylinder, right? You go up and down, the distance from the z is always exactly 3. So that's kind of a simple way to represent that one. Another one is this right circular cone. In this particular case, x squared plus y squared equals z squared is your Cartesian, but r equals z is the simplified cylindrical coordinate system. And that's just telling you that at any given point, the distance from the z-axis is the distance, is the height. If the z value and the distance from the z-axis are always the same. That would be true coming out of the board or going into the board as well. And that produces a cone, which makes sense because you kind of have a line. If you think of r equals z, it's sort of like y equals x. You have that projection line there. This one is one that makes a lot more sense to represent in cylindrical coordinates, however. And that's this idea of theta equals some value. And all that means is that it's not specifying what the z value is. So that creates that, that cylinder idea, right, where we have it just creates a plane. But all it's taking is what you might think of as either the xz, well in this case it's the xz plane, and it's just rotating it some theta. So you can think of that plane as just the points that all have some theta value, because r can go to infinity, so it goes out all the way along, and z can go to infinity, so it covers the entire plane at that offsetting angle. And then finally, we have a case where it doesn't matter. In this case, z is some fixed value. Well, that's just the raised plane. That's the xy plane shifted by some value c. And there's no difference in either coordinate system on how to represent this because z equals a number would be the same in either coordinate system. So we're going to do some examples of converting back and forth using these relationships that we developed in the previous section.